Okay, you can start.
Okay, respected professors, colleagues, and dear participants, a very good evening to all of you. So, on the behalf of the Department of Physics and Astrophysics, I welcome you all to this colloquium on functional nanophotonics, order to tailored disorder. Our speaker for today is Professor Rajesh Nair from IIT Ropar. This colloquium is being organized by the Indian Physics Association as a part of online monthly colloquium series on recent development in scientific research activities in physics and their applications. So without further ado, I would request Professor Sunil Kumar, Head Department of Physics and Astrophysics, for a welcome address and for a brief introduction of our department, physics department. Sir, please, over to you.
Thank you, Dr. Minu. I'm audible?
Yes, sir, you are audible.
Hello?
Yes, sir, you are audible.
Okay. So, respected Professor. Sorry?
I think you have a bandwidth issue.
Audible or not?
Yeah.
Hello? Are you able to listen me?
Yes, sir, but sir, your voice is
Hello?
not clear.
Maybe you can switch off the video.
Okay. Now?
Yeah.
Is it clear now?
Yes, yes. Please go ahead.
Okay. Okay. Thank you, Dr. Minu. So, respected Professor Sunita Shrivastava, Professor Vandana Nanal, Dr. Minu Thakur, Dr. Jaswant, Dr. Ramavtar, my colleagues, participants, and dear students. This good evening to all. Very good evening to all. So, on Department of Physics and Astrophysics, I welcome you all in today's lecture. And I would also like to thank Indian Physics Association for providing us this opportunity to host this colloquium. Our department, which is Physics and Astrophysics Department at Central University of Haryana, was established in July 2013 with Master of Science course, Master of Science in Physics subject. And it was a part of School of Physical and Mathematical Sciences. Later on, now it is a part of School of Basic Sciences. And right now in our department, we are having 6 regular faculty member, where we have 2 professor and 4 assistant professor working in different fields like astrophysics, nuclear physics, material science, thin film technology, uh, and all these faculty members are working consistently and publishing research work in various journals of good repute. And also, I would like to mention that our department has published 2 patents and also submitted 3 more patents in the for Indian Patent Agency. The department currently is offering integrated BSc MSc program in physics with 30 student intake, MSc physics program with 50 student intakes. So, and also PhD physics, PhD program in physics. Right now, we are having about 100 MSc students, 30 student in integrated BSc MSc physics course, and 18 PhD students. And the department is working under the guidance of these all our well qualified teachers. Students are able to qualify various national tests like GRE, CSIR, NET, JEST, GATE, etc. And even this time, our I think about 15 students had qualified NET and GATE exam. And since our PhD started in 2019, we expect that within 2-3 years we will be able to publish good number of papers in the research journals. And soon, as Dr. Vandana Nanal said, we will be having offline colloquium at Central University of Haryana. So with these words, I thank you all. And over to you, Dr. Minu.
Thank you, sir. Now, I would like to invite Professor Vandana Nanal, General Secretary, Indian Physics Association, to say a few words about IPA and its activities. Please, ma'am.
You can see my screen?
Yes, ma'am. It's visible.
Okay, 1 minute. Yeah. So, first of all, thank you very much for hosting this IPA colloquium. And let me just take, since there are many students in the audience, I will just take a few minutes to introduce Indian Physics Association to those who may not know about it. So Indian Physics Association was founded in 1970, more than 5 decades ago, with a goal to help the advancement, dissemination, and application of knowledge of physics. It is achieved through publication of bulletins, reports, newsletters, informing of new developments, and arranging seminars and special programs, lectures, particularly for students, teachers, and young researchers. So if you see here in this cartoon, the shows a typical bird's eye view of the IPA activities across the country. There are more than 40 chapters and more than 4,000 members spread all across India. And we organize several lectures. Annually, we have a DAE CV Raman lecture series. 5 lectures are organized. Additionally, we have IPA, IOP, UK, Bhabha Cockroach Walton Exchange lectures. These lectures are alternately held in India and in UK. In India, they are called Cockroach Walton lectures, and in UK, they are called Bhabha lectures. We have Professor P.A. Pandya Endowment lecture annually. These lectures are organized at different universities or colleges in India. In 2020, as you all know, we were hit by the pandemic, and IPA's 50-year celebrations also went online. And we are right now using also that to our advantage to go to a much wider student audience and to different places. So in addition to this, IPA gives awards biennially for recognition of senior and young scientists, and it liaises with other national and international societies. The quarterly bulletin, which is published, which is the Physics News, is available online on the IPA webpage, and more information about IPA can also be found on the IPA webpage. The Physics News brings out special issues from time to time. We have also brought out issues showcasing works of women scientists or renowned Indian scientists like Meghnad Saha, S.N. Bose. And the present issue, which will be released in May, will be on the climate science. So the current office bearers of the IPA are Professor S. Ramakrishnan, Director TIFR, who is the President. Professor Tanushree Saha Dasgupta, Director SN Bose Center, Kolkata, is Vice President. I am General Secretary. Professor Samit Mandal from Delhi University is Joint Secretary. And Dr. Aradhana Srivastava from BRC is Treasurer. IPA set up a gender group for working group for gender in physics to address the specific problems about gender inequity in physics profession in India. The current chair of this group is Professor Shubhavati Goswami, PRL. So if you would like to join IPA, now it's fairly easy. You just go to the IPA website and there is a registration link. You can go to the new registration and fill up the registration form. We have a student, annual, and life membership. Your form needs to be forwarded by one of the life members of the IPA. And then you will receive information for the payment and so on, but it will give the information about your educational purpose. If you want any additional information, please write to one of these email addresses. I'll put them in the chat box also. So after this successful webinar series, New Horizons in Physics, on the occasion of IPA's Golden Jubilee celebration, we started the online monthly colloquia series. This is typically held on first or second Saturday of month, depending on the holiday and the availability. The focus has also been innovative technology and applications to see the applications of physics in different parts. And you can see there were a few talks by entrepreneurs who are also have gone into different dimensions. We also had talks on the Nobel Prize 2021 by Professor Srikant Shastri on Parisi's work. And in the same way, today we have Professor Rajesh Nair, who has been, who has also recently featured in the list of 75 promising young scientists, which were brought out this year by the by DST and the PSA. So most of these lectures of the IPA are available on the IPA YouTube channel. So please visit and enjoy these lectures. Please write to us if you would like to hear anything more from us. And without much further ado, I hand it back to the organizers. So let me thank Department of Physics and Astrophysics, Central University, Haryana, for hosting this lecture. And of course, to speak, I look forward to an exciting lecture. Thank you.
Thank you so much, ma'am, for such a nice introduction. So moving ahead, I request Dr. Jaswant Kumar, Assistant Professor, Department of Physics and Astrophysics, to formally welcome and introduce our esteemed speaker. Over to you, Dr. Jaswant.
We may have
Hello?
we may have to unmute him because I have not.
Okay, thank you very much. Thank you very much, Dr. Meenu. Thank you for giving me the opportunity to introduce the speaker for the day. So here is a brief introduction to Professor Rajesh. Can you all hear me?
Yes, sir. Yes, you are audible.
Okay, good. Yes. So Professor Rajesh Nair did his BSc in Physics from Kerala University, Kerala in the year 2000. Thereafter, he finished his Masters from Mahatma Gandhi University in Kerala in the year 2002. After finishing his Masters, he went to Mumbai to get his doctorate in philosophy from Indian Institute of Technology. He finished his doctorate degree in 2008 and thereafter went for a postdoctoral fellowship at COPS, University of Twente, Netherlands. He spent 2 years there and did some of the fundamental works that he shall be discussing at that place. Thereafter, he joined as K.S. Krishnan Fellow, the Bhabha Atomic Research Center from 2010 to 2012. He also worked for a short period as Scientist D at BARC. In the year 2013, Professor Nair joined as a faculty member at Indian Institute of Technology, Ropar. Coming to the research contributions of Professor Nair. Professor Nair has made notable contributions in the field of nano-optics. For the benefit of students at our university, I would like to tell that nano-optics is the study of behavior of light on nanometer scales. It also studies the interaction of nanometer scale objects with light. Dr. Nair's work involves observation of sub-Bragg diffraction. I'm sure he will be telling a little bit about this, of waves in crystals. His work points to the signature of three-dimensional photonic band gaps and lasing from nanoscale photonic structures. Professor Nair's scientific findings are published in high-impact journals, and they are highlighted in international scientific magazines. Some of them are like Nature India, Science, Optics and Photonics News of Optical Society of America, etc. Professor Nair has also been a recipient of some of the important prizes, some of them being the K.S. Krishnan Fellowship from Department of Atomic Energy, National Academy of Sciences of India, NASI Young Scientist Prize for Physical Sciences in the year 2012, also the Indian Science Congress Prize in Physical Science in the year 2011-12. Also, as Professor Vandana just mentioned, he has also been a part of the top 75 scientists, physicists working as declared by DST recently. It's a privilege to have you, Professor. It's a privilege to have Professor Nair as the speaker today. The title of the talk is Functional Nanophotonics, Order to Tailored Disorder. I'm sure the talk will generate a lot of scientific curiosity amongst the undergraduate, research scholars, and faculty members of our department. It's over to you, Professor Nair.
Okay, ma'am. Thank you for the introduction. Let me share my screen. Can you hear me?
Yes.
Okay, so I think my slide is also visible.
Yes, it's visible. Yes.
Okay. Okay, so again, good evening to all of you, and I especially thank IPA for these invitations, and also to the Central University of Haryana for hosting this lecture and for the nice introductions. So as requested,
Rajesh, is
yeah,
it possible to keep your video on, or do you have a bandwidth issue?
I can keep it, but I'm not sure any issue comes. Okay, let's go ahead.
In case issue comes, then you can switch off, but otherwise it may be nice for students to
Yeah.
see. Thank you.
So the talk I prepared, aiming at master and BSc students. So I try to make it as simple as possible without much mathematics and things. I'll be trying to explain you some of the concept of nanophotonics using many pictures and cartoons. Okay. So the title of my talk is a functional nanophotonics. So order to payload disorder. So I'll show you in the next 45 minutes or so how the light interact with some of the ordered structures or the disordered structures, but at the nanometer or micrometer scales. So I'm from the Department of Physics at IIT Ropar in Punjab. So in the slide, you see a nice picture of peacock feather. I'm sure everybody in the audience must have noticed at some point in your life. And this is one of the best examples of a nanophotonic structure in the nature. Okay? The color you see is because of the structure inscribed on these feathers or the barbels. And the right side, the measurement we did in our lab on a peacock feather. And you can see that there are, it's a reflectivity as a function of wavelength. So you can see that at certain wavelength, there is a reflectivity strong for different positions on this peacock feather. And that is why, because of the strong reflection of light, you see a very beautiful coloration in the peacock feathers. And there is an altogether research in nano or in the optics community, what is called a bio-inspired photonics. So basically looking at these kind of structures and learn how nature produced these colors and try to mimic them in the laboratory for not only fundamental physics, even for a technology. Even the Helvet Pact, HP has a dedicated research group focusing on these kind of activities to looking at the technological perspective. So you'll probably understand on the way how this light reflection happens and more about these things. So this is the outline of my talks. I'll briefly introduce you in nanophotonics, and I'll take one important aspects of nanophotonics, or one of the important stuff in that big umbrella, which is called photonic crystals. And I'll introduce you photonic band gap, and I'll tell you how we can use it to control the emission properties, the spontaneous emission properties, why the system is so exciting. And at the last, I'll little touch upon how to introduce disorder in a quite controlled way, and how we can make a comparison between ordered and these tailored disorder samples. So what I'm going to talk is the left side is of the ordered system. So you can see that there is some ordering here everywhere. And the right side, also there is some, you cannot see the nice ordering. It's quite a disordered like a system. So on the way, I'll talk about all these things. Okay, so nanophotonics in general basically mean the light managements. So you make structures of the order of nano subwavelength scale, both using dielectric or metals, and depending upon how you structure them, what kind of symmetry you have, they will interact with the light in a very different way and give a different perspectives. And we manage light. Everything is about light, how we see, perceive our life, or we enjoy our life because of the way the light can be managed and how. So basically, with the advent of semiconductor era, then we have a photonics technology era. The lasers are developed, the fiber optics was developed, which changed our life itself, right? Everywhere you go, from a bar scanner to a internet, now we are all doing this because of fiber optics. The optics was really tremendously developed in a very technological point of view. But then there is a need that traditionally we do all this with the big lenses, mirrors, large scale systems. Then there is a need to how to find different sources for better efficiencies and sensors and many more applications like in the quantum technologies and all. So from the traditional optics side, people thought in the last few decades, what happens when you have a structures of the order of the wavelength of the light? So that actually create the birth of nanophotonics. Basically, if kind of a definition, if you want, a creation and manipulation and detection of light at sub-wavelength scales. So basically, you take materials and you structure them at the nanometer of sub-micrometer scale, and which can help you to confine the light. You can slow down the light, or basically you can play with light. You can do whatever function you want to do with light. and it has many applications in telecommunications, in medicines, and this coming up in quantum technologies, where the nanophotonics has a big role to play in many requirements. Okay. So when you look at nanophotonics, as I said, light management, first and foremost, you need to make structures. You need to identify what kind of structure you need to make with depending upon what functionality you look into that. So keeping that in mind, so people looked at structures like this. Resonance basically try to make a strong interference at subwavelength scales. And there are also structures which can use to have a back scattering for the back diffraction for light waves, not for the X-rays. And that will give very interesting application, quite similar to condensed matter system, but it has a marvelous prospects in light emission controls. And there are also system people have made what's called a multiple scattering. So you make the light to have a kind of scattering within the system so that it spend more time so that the light matter interaction can be enhanced. And in all these pictures, you may notice one thing, things are quite periodic, right? So here also there is some ordering, here also there are ordering, and things are quite beautiful because it's arranged so nicely and periodic. And this periodicity of the order of half a micron usually, or depending upon the wavelength at which you wanted to make the system work. Okay, and I'll tell you on the way how we design and how the physics behind all those things. Okay, so if I had to, I'll tell you how this field come up historically, then I will take you to a technical slide deep into the physics problem. So this is purely in my opinion. So if you look at how light or the wave interactions happens with any kind of periodic structures, it all started with the famous paper by Lord Rayleigh in 1887. So what he considered is a laminated medium. A laminated means is a periodic medium in which the mechanical properties are periodic function of one of the coordinator. So basically, you have a periodic medium here. Let's take this is a variation of some Young modulus or refractive index. So you have a black, white, black, white. So he considered a periodic system. And why he wanted to do that? He wanted to understand why the certain thin plates, certain system will give a color, why it reflects some particular wavelength very strongly in comparison to others. And so he went on to say in this paper, so these are all the text which I written from his original paper. Okay, so you can see the difference in the English. Okay, so the wavelength of a train of progressive wave means the wavelength of the propagation light, the light propagate through the system is equal to the double interval between the loads, basically the periodicity or lambda equal to 2D. There will be a result in a powerful aggregate reflection. That means when you have system where you make lambda equal to 2D, the system becomes strongly reflect light. Similar to your Bragg condition, you mostly students all studied in condensed matter physics, that when you have m lambda equal to 2D sine theta. So what I'm talking is that lambda equal to 2D condition when theta equal 90 degree in that case. So you have a strong diffraction. So even though individual contribution by the different Bragg plane is smaller, so it interfere coherently and you give a very strong reflection of light or reflection of waves. So the Rayleigh actually, without even mentioning this in his paper, has already talked about a frequency gap possible. When I say frequency gap, absence of frequency through the medium in 1887. And after this, the Bragg diffractions happens in around 1930s, which you already know from your books. I will keep it in the perspective of nanophotonics. Then from 1887, I now take you to 1935. Most of us, many people may not be aware of these two works. So in 1934 and 35, our own Professor C.V. Raman has written two papers in the Proceedings of Indian Academy of Science. So in one of the paper, he was quite interested, like Rayleigh, why certain birds shows colors, the origin of the colors in the plumage of birds. Like why certain colors, and he classified in 1935 the colors can be two types. One is called iridescent type. That means the color change when you view the sample, like you take a CD in your hand, you just rotate it, you can see different colors coming. Those are called as iridescent colors. And colors can be non-iridescent color, like colors in your shirt or in a flavor, or for example, whatever way you look at, the color remains the same. So he was quite interested why this thing happens, and he also interested on these kind of seashells, so a very nice beautiful colorations, and when you rotate them it shows different reflection of light. So he also talking about the laminated structure of this substance. So underlying feature is that all these structures have some kind of periodicity inscribed in it, and that's the reason why these colors. And unlike papers, research papers now, if you really see this paper, and you can see that these papers are without any graphs or without any pictures, unlike a nanophotonics paper of the present day, where a lot of colorful, nice pictures and things like that. Okay. So this is about 1935. So may not got much attention because it was not talking in a technology rather than looking at how the colors happens in some natures and try to understand that interference process. Then in 1917, after this, the lasers are invented, and there was a demand to control the spontaneous emissions because that contributed to the loss into the lasing system. So around 1970s, there was a paper published by a Russian scientist, at that time it's Soviet Union, but titled is Spontaneous Emission in Periodic Structures. So from the laminated structure, word is now become periodic structures. And what he is trying to say, we have a periodic structure. For example, there is a periodicity, the periodic air holes in the system. You have a system like that. Don't worry too much. I'll tell you everything in very detail. So you have some kind of periodic structure. You keep an emitter, which is this emitter, which is emitting light in all directions, like the bulb in your room. It's an isotropic emissions. So he said spontaneous emission of an excited atom in a periodic structure is considered. So after the laser, people wanted to see whether it's possible to control spontaneous emissions to get a much low threshold lasing and such process. And this was also not that much noticed. Then there was a paper in 1981 from MIT by Daniel Kleppner. You can see the title from the spontaneous emission in periodic structure. Now it's changed to inhibited spontaneous emissions. Okay, so how to stop spontaneous emissions? Like if you studied in the time-dependent perturbation theory, that spontaneous emission is something which cannot be controlled, like as shown by the Fermi's golden rule. It happens because there are vacuum fluctuations, and there is no way you can have it be there. So he considered a system. You trap these kind of light sources in subwavelength cavities. Cavity means you have two kind of mirrors, and you trap the light source in between them, and you're probably able to control the light emissions, or basically spontaneous emission. And this was another work which was an attempt to create the emission control. Then a landmark paper published in 1987 by L.I. Ablonovich, and this is a nice paper to read without any mathematics or much graph. It's like telling a story to you. And he has considered that from the Bell Labs, the title Inhibited Spontaneous Emission in Solid-State Physics and Electronics. Instead of having these kind of periodic structures, if a three-dimensional periodic structure has an electromagnetic band gap overlap with the electronic bandits, the spontaneous emission can be rigorously forbidden. So this was Bell Labs at that time trying to develop high efficiency semiconductor lasers, and it was an attempt to how to control the spontaneous emission in those lasing devices. Put this paper into the public, and this paper is, I think, the highest cited paper in PRL, more than 20,000 citations. So this paper actually come up with the same thing what Rod Rayleigh or what C.V. Raman trying to say, instead of how these colors come in the system, but they come up with an idea how to use this color generation to control a spontaneous emission of light sources, and in a way try to make a technology out of that to make fast light sources, and even in the present day quantum technologies to get high emission rate single photons. Okay, so this is the way historically developed in the field, the nanophotonics, or in the photonic crystal field is developed. So let's now move to a little bit of technical, what is the things hidden behind, what is the secret behind all those things. And I'll start with something which you already know about it. So you studied when we application of quantum mechanics or in the solid state physics, we start with the Schrodinger equations. And we say Schrodinger equations in a free electron model or a potentially zero, you solve it and you get a dispersion relations or the energy versus momentum relation. And you have this parabolic relation between the energy and the momentum or the frequency of the momentum. So what we study next in condensed matter physics is you have a periodic system. You have a same electron or the de Broglie waves in a periodic system, which is nothing a semiconductor crystal, where the atoms are periodically arranged. And this periodicity of the atoms will give you a kind of periodic potentials, and you have this Corning-Penny model and so on and so forth. You are studying in condensed matter systems. And when you solve this, we're doing a lot of mathematics, you can plot the energy versus wave vector relations, the same dispersion relation. And what you get is the gaps in the energy levels and the energy band gap. So you call this a band gap. And this band gap arises because the de Broglie waves satisfy the Bragg conditions at k is equal to pi or k is equal to 2 pi, and you have a energy range where there's a wave is not allowed through the system, right? So you have a band gap, And within the band gap, there is no solution possible. The wave vector is imaginary, and the waves have a decaying nature. Now imagine if I want to do the same thing with photons. So you have a band gap for electrons or the de Broglie waves here in a semiconductor, and that origin of that is due to the periodicity in the atoms. So I want to do the same thing for a photon. So basically, can I have a semiconductor for photons or a band gap for photons? Now, when I talked about photons, obviously we had to solve with Maxwell's equations. And when light interacts with the material, the quantity which arises is the refractive index. So whenever light goes from one medium to another, what you look for the changes in refractive index, the reflection, the transmission, the phase change, everything is dictated by the changes in refractive index as the light propagates. So we have to solve using Maxwell's equation instead of Schrodinger equations. So you take, again, in electrodynamics, we start with Maxwell's wave equations. Then you take a free space, which is a vacuum, and you solve, you get a wave equations. And if you plot the dispersion relation similar to what you did for Schrodinger, the frequency versus wave vector, it gives you a straight line. That's what you study in the basic electromagnetism, right? So you start with electrons in free space, you got a parabolic dispersion. I start with the light in free space or the vacuum, we get a straight line relationships. Now I want to see when you put this light in a periodic system, what kind of how the solution is going to come. Okay. So in the case of semiconductor, the band gap arises because there is atoms are periodic, and like in the case of light, if you want to do something you want to get a similar kind of band gap for light, you need to structure the material at the scale of using refractive index. So that is what is called a photonic system, and the same system which is considered by Rayleigh or the later by C.V. Raman and all this. So basically, so you have a periodic system, the variation of dielectric constant epsilon1 and epsilon2 in one directions. Okay, so when the light comes from the left side to the right side, and the light sees this periodic modulation in the refractive index or dielectric constant, and because of that periodic corrugation or periodicity in the structure, the light gets diffracted, similar to X-ray diffractions. And the wave equation, which you usually see in the books, has dielectric constant is constant, but now the dielectric constant is a function of space. So that's why the mathematically tedious to solve, and then there are numerical codes to help you with that. Okay. So when you send the light into the structure, so light gets reflected from each of these interfaces, and if you rightly tune the sample, the reflected light interfere constructively, and you get a very strong reflection of light. And this light, which will be absent in the transmission. That is what is called a frequency gap or a band gap for light in this direction of propagations. The light, this band gap depends on angle because this is an interference process. The moment you change the angle, the condition will change, and it also depends on polarization of the light. So if you look at if you solve a dispersion relation for a periodic system like that, like a semiconductor you did in your books, you plot the frequency versus wave vector, and you seems to get a gap in frequency at a wave vector pi by a. And why pi by a? That is a wave vector where you satisfy the Bragg condition for the light. So if you take this kind of structure, if I give you this sample like this, and you launch a frequency of the light within this yellow region, the light cannot propagate to the sample. And this absence of propagations, which the light does not allow it to pass through it, we call it a band gap or the frequency gap or stop gap. And I use this in intermittently in the top. They all mean the same. Okay. And so what happens to the light? It just decay into the structure. It's like a bracket. And you can have this periodicity in 2 directions and 3 directions. And you can have a similar to a semiconductor where you have a band gap. Here you can have really a photonic band gap system. Now people can argue. So we know already everything in X-rays. Now you are just moving to optical wavelength scale. What is more attractive about it? Why it is so exciting? So I'll come to that bit later. Okay. So how do you know that if I give a sample, it has a band gap for light or not, or what we do experimentally or things? So what we need is you have to measure the reflectivity and transmission of the light as a function of wavelength. So you can see that the reflectivity spectra, which is a calculated reflectivity spectra for these kind of 1D samples. So you can see that there is a peak in reflectivity, around 100% reflectivity. And at the same wavelength, you have a 0% transmission of light. That means the frequency or the wavelength which falls within this range does not propagate to the system. Okay. And this band gap position depends on the refractive index contrast. That is the difference between epsilon1 and epsilon2 in my previous slide. And the maximal difference you get, we have the very strong light matter interactions. And if you look at the field intensity with at this inside the structure, suppose if you're launching a light at this wavelength around 1500 nanometer, and you look at how the field decay into the structure, you can see that a field has an exponential decay into the structure. And why it has exponential decay? Because this is the band gap wavelength, so the light cannot propagate into the system. It has actually damped into the system. And it propagates into the system because it's an interference process. It goes and reflect back, and interfere constructively. So this is a kind of a signature of a photonic band gap if you measure it. And in all this analysis, all this presentation or all this work, we try to we keep absorption is 0 in the system. Okay, so the absence of transmission is not an absorption, rather it is a reflection of the strong reflection of the light at the designed wavelength. Okay, and you get these kind of nice fringes here. These are because of interference, the thin film interference. You have nice fringes, and these fringes width and strength depends on thickness and refractive index, like any basic optics you studied. So you can estimate the thickness, and which is a very nice way to get the sample thickness. I'll show you the real samples later. So what I introduce is a band gap for photons and how we understand that, and using a one-dimensional system. But we can also have this periodicity in dielectric constants in two-dimensional, three-dimensionals. So this is basically a two-dimensional photonic crystal where you take a sample. For example, you have a silicon wafer or something. You have a drilling machine. Now you make holes. You make periodic holes. And periodicity, we are talking of 300 nanometer. And the diameter is also of the order of hundreds of nanometers. So, okay, so it's as simple as that. You think you take a material, you make periodic array of holes of the periodicity of the order of 300 nanometers. So this is a real sample picture that people made in the laboratory in a silicon wafer. You can see that there is a nice periodically arranged refractive index variation. All these black regions are air, the material is removed, and the gray regions are the silicon. So when the light propagates from the left side to the right side, it does see this variation in the refractive index. And when the light goes from, let's say, top to down, you still see a variation in the refractive index contrast. And that is why it's called a two-dimensional photonic crystals. That means if I launch light from this direction and this direction, I should get a band gap for light. And now I can think of same thing in a 3D periodic system. And this is one of the champion structure which people predicted in 90s and which was experimentally measured in 2011. Okay, so this is a cartoon picture where you take a box, you drill holes in this way one, and you have another holes in this way. So these are two interpenetrating holes, and that make the system a periodic in 3 dimensions. And this is a real sample picture. The top is cut to show you that how the pores are well connected within the system. So here the one material is silicon, the other material is air. So it's a variation of silicon refractive index and the air refractive index, which is 3.5 and 1. So any direction the light propagates, it does see this periodic variation in the refractive index. And you will have really a band gap for light because it gives you in all the spatial directions in the band gap for light, or what we call is a photonic band gap. Now, the take-home message, what you should understand, a photonic band gap is originate because of the periodicity in refractive index. And this periodicity in refractive index happens at the optical wavelength scale. You can have it near infrared, you can have it microwave, and it depends on where you like to have your band gap and depending upon your interest and applications. And these are mostly man-made structures. Unlike a semiconductor, you don't need to keep an atom by yourself, but here you have to really make the structure. So experimentally, it was become a really challenge to make these structures and measure these things. And even photonic band gaps still remain as a challenge for people to measure. So you have a periodic system, and you send the light from outside, this kind of arrow, and the light get reflected. You send from this, it reflected back. If you send in this direction, it reflected back, and from the bottom it reflected, and from the left side also reflected back. So that means you have a system the light cannot go in. It's like it's not allowed. You don't have a passport to enter whatever door you take. Now I wanted to think a thought experiment, a reverse of this. Suppose I keep a light source inside. I have a bulb inside, okay, or I have a laser inside, whatever it is. I have a source inside, and you give some energy. I put the switch it on. it start emitting the light. Like when you put a switch on the light in your room, it start giving isotropic emission. The light comes in all directions. And it tried to propagate to the outside world, like the way light propagates, right? But I put a one condition for you. The band gap wavelength is equal to my emission wavelength, right? So I have a system which has a photonic band gap at certain lambda, and I want to keep a light source inside that material with the emission lambda is same as band gap lambda. So now you can imagine this light emitted, it's trying to propagate to the outside world, but it cannot go out because of internal Bragg diffraction, because this is also light wave. It sees these periodic variations and it has the internal Bragg diffractions. So this way you can control the spontaneous emission of light sources. This is what the Jablonowicz famous paper in 1987 all about. So if you think that three-dimensionally you have a band gap system and you have light source inside, no way you can get the light out. It will be internally Bragg reflected. And I'll show you later how we do experiment, how you check whether it really works or not. Okay, so this is, and because of this, what the photonic band gap got a lot of interest, or the nanophotonics become extremely popular, because now you have a very nice dielectric system where a spontaneous emission can be fundamentally altered. Not only is interest in physics, but it's also have a lot of technological application like high efficient lasers, or you can make emission isotropic, or put it in, sorry, anisotropic, and you make it in a very strong and particular direction. So if you look at photonic crystal, so the light you send from outside, it cannot propagate, it reflected back. I keep the light source inside at the same band gap frequency. The light cannot propagate in the band gap frequency because it has internal drag. And if you calculate the density of states, the photon density of states, like you have electron density of state you studied in condensed matter after the band gap theory, and at the band gap you have a density of state goes to 0. This is what you studied in condensed. Similarly, here also you have a band gap, but at the different wavelength scale, you expect to have density of state is also be 0. So if there is no periodicity, the density of photon state has an omega square dependence. And because of the band gap, you get a 0 density of states. And now if you have a system where you can generate a density of photon state is 0, and you look at the Fermi's golden rule. In quantum mechanics, the decay rate, suppose you have a 2-level system, you excite an emitter, and the decay of that emitter, the 2-level system, depends on a term called rho, which is the density of photon states. So now I have a system where the density of state goes to 0, and that means theoretically or ideally, I have a system which has a decay rate is 0, and decay rate is inversely proportional to lifetime. So I have an infinite lifetime. So I can inhibit the spontaneous emission of light sources using photonic band gap. So this was essentially the idea put by Jablonowicz and others to achieve low threshold lasing or the thresholdless lasing, so that you have no spontaneous emission, or you create a cavity to enhance the emission of light. Okay, so I'll show you later how we do experiments. So now is a big challenge. How do you make this sample? How do you make these structures? Even theory, if you look at really the nanophotonics theory is quite advanced, but making these structures are really a challenge. And even if you have a very nanofabrication lab, it has a very difficult to get the periodicity without much defects and a very nice sample. So we use another technique, which is a very simplest technique. We can easily do it at Ropar. So the chemists are well mastered on making colloidal particles, even before nanophotonics arises. So they're very mastered in generating silica or polystyrene spheres of diameter of 300 nanometer or 500 nanometer. And nowadays, commercial companies even sell it. You can just buy from market. So we brought these kind of particles. These are sub-micron polystyrene particle. Diameter is around 280 nanometer. And we did a lot of recipe by trial and error. We optimized the growth. And we have this colloid spread in the suspension, and we keep a glass slide. And you kept this in a controlled environment, basically a temperature controlled oven. And after a few days, the water gets drained off, and this will form a self-assembled crystal on a glass substrate. So we don't know much chemistry, but we learned by trial and error, and it works for us. And it's quite repeatable for different diameters and different spectral rates. So after 4-5 days, you have a very nice crystal on a glass substrate, which you can hold in your hand. Okay, and this is quite popularized in the 90s and 2000 by these couple of papers, and we just learned from this and make it. So once the sample growth is done, you take the sample from this beaker, and the sample will really astonish you. The sample look like this. If you put the sample in the tube light in the laboratory, it nicely diffract the light. And this color you see because of the sample reflecting around green light, which is a band gap for this sample. So the green light cannot go into the system, so it reflected back. And this is exactly you see in peacock feather, which I showed my first slide. So imagine different kind of photonic crystals stacked together, you will have a very beautiful coloration, you can see that. And this color, as I said, depends on diameter of the spheres or the refractive index of the material. And if you slightly tilt the sample, you see a bit of orange or yellowish colorations. So you have a different colors, you can see that. So because it's an angle dependent. So once you have the sample, you can see that like you don't see X-ray diffraction with your eye. But here you can see Bragg diffraction of light waves with your eyes. You don't need even a detector to see that, yes, indeed light is getting diffracted. And so once you get the sample, you need to see whether it has a, how the ordering is happening. So this is a helicopter view of the sample. Look like a cricket pitch because during the sample growth, it got all these cracks and things and it become like pieces. And is a image of the sample. If you take some small region here, it look very nicely ordered. Usually people show these kind of pictures, you think that everywhere sample look like this. That's not true. You have a lot of defects, a lot of cracks, a lot of bad things also happens. Okay, so this is a kind of a crack. You can see something like this crack. You can see that on both sides of the crack also, it is nicely ordered. And this is a crystal, as I said, so it has some symmetry about it. And these crystals have a face-centered cubic symmetry, and the Brillouin is shown here. And this is a zoomed image of the sample. You can, if you look at closely, you can see the top layer, and below that, the second layer is also grown very nicely. And this is one type of symmetry of a photonic crystal people use. There is altogether a different type of symmetry, which is like a diamond-like symmetry, which making these samples are extremely difficult and which is not possible with us. So, but few groups only, I think 4 group in the world is able to make these kind of samples, which is on using silicon silicon wafers. Okay. So once you make a sample, how do you characterize in the lab? So as I said, we need to see whether it has a band gap or not. So we do an experiment. We measure the reflectivity as a function of lambda, and simultaneously we measure transmission. So the reflection shows a high reflectivity around 600 nanometer. And if you look at transmission, which is a red dotted curve here, the transmission also drops and become close to zero transmission, then rise up and goes to the high value. So if you take the sample, and if you launch a light at 600 nanometer, it cannot propagate because close to 60% of light, it is reflected back. So you said that, okay, my sample have a direction dependent band gap because you are only looking at one directions. And if you change the angle of the incidence, this wavelength will shift it because it is an interference process. So we make this kind of sample quite a lot. I think around 6 or 7 samples. You can see that if you have a lattice constant is basically the sphere diameter, it's close to 300, you get a band gap here. And if you increase the lattice constant, the band gap frequency also increases. So if you want at 500 nanometer, you need to use this lattice constant. If you want at 1800 nanometer, you have to use this lattice constant. It's a scalable with because it's an interference process. And we calculate a band structure, the dispersion relation, and you can see that it's nicely compared with our experiments. So indeed, we have a nice result, and your system actually show a band gap for light. And this is angle dependent, polarization dependent, and it gives very interesting light matter interactions, which I'm not discussing today, but probably you can look at this paper if somebody's interested, and we published quite a series of papers on these things. But what is now if people working in this field, the critic will say, yeah, fine, you got it, but the reflectivity is just 55%. Ideally, it should be 100%, right? So your sample is only giving a 60% reflections. And that probably due to the large number of these unwanted cracks and defects. So now, can the system give a reflectivity of 100%? So we look at the sample, and the reason is that when we do this kind of measure, we use a light beam of this order of 5 millimeter. So 5 millimeter sample on your 5 millimeter lights on your sample. So that means it is actually mapping all these dirty things in the sample, all these cracks, all these point defects. So the light is reflecting in all directions. So now the question is, can we measure from this small region, which is just 100 by 100 micron or even less than that? And no commercial technology, no commercial setup will help you. So you have to build your own facilities for that. And that's what we did the first thing in the after this in Ropar. We developed a setup what we call micro reflectivity setup. It's published. You can look at how you make this instrumentation. The whole beauty of this system is two. One is that we can go down to a small area of the sample and you can collect the signal from there. The second is that you avoid the chromatic aberration in this setup, because when you do a wavelength dependent measurement, you want all wavelengths should focus on the sample at the same positions. So you want to avoid the chromatic aberrations. So that is also taken care in this setup by using a lens, which is not a typical lens we use in the laboratory like a glass lens. It's like rather you use a reflection, use the curved mirror and focus on the light on the sample. So we developed this setup and let's see whether it will give 100% light or not. And we measured by looking at one spot on the sample, and the blue line is our measurement. And you can see that it's nearly touching 100% reflectivity of light. And the conventional measurement, which you see in literature, even we also did before we having this setup, is comes closely 50-55%. So this kind of nice optical instrumentations can help you, even though your sample is not that great, because your colloidal systems are less index contrast. So you can use it for many fundamental studies. And what is more interesting, we found out that you can also get nice these fabric pore fringes, which I zoomed here. And from there, you can find out the thickness of each of these domains. And these interference fringes will give you the thickness value, because you know the refractive index value. So you can put in interference conditions and you can estimate the thickness. So you can see that our sample is actually having a huge variation in the thickness. And this variation thickness is actually a really game changer for these photonic crystal samples, which probably I'll show you. I'm really running out of time. Now, the thing which I showed you in the very first slide. So we have this peacock feather. We took it, we got it, one student brought it. And you have look at our camera in our setups. You can see one barbel. If you take one barbel of a peacock feather, it looked like this. And this is the laser is focused on in our lab on one barbel, and we measure the reflectivity. Now you can see that this peacock feather also giving a peak in reflectivity, and that happens because this peacock feather has a photonic band gap, and this photonic band gap actually arises because of the periodic structure put upon these peacock feathers. So it's a very nice natural nanophotonic system, which give you this kind of nice collection. There are many papers published when people use Maxwell's equations, solve peacock feather and find solutions where you can get a band gap for the light. So that is, so we have a system, we send the light from outside and we see, okay, my system have a very nice band gap. But that is only a frequency scaling from X-ray diffractions. Do my sample show you a control in spontaneous emission of light sources? So for that, what we did is we put the emitters in these samples everywhere. Basically, each of these spheres containing a dye. Dye is a rhodamin bead dye, and which is attached with all these microspheres. And so emitter is present everywhere. And then we develop a setup to collect this emission experiment. So basically, we are collecting photoluminescence of light. So we have a sample. We take a laser, which is 532 nanometer. And why we use 532? Because that is the absorption of the dye. So this light is excited dye molecule, which absorb the 532 nanometer and emit around 600 nanometer. Okay. And so emitted light is collected and sent to a spectrometer, basically a grating, and collected by a detector. And these we did measurements initially by using a lens from the large area and also within a small region within what is basically within a domain. So before doing measurement, first we look at the intensity versus wavelength for a dye, the reference sample, okay, which is a dye suspension. And you can see that it gives a nice photoluminescence or spontaneous emission around 600 nanometer. And then you measure this, you trap this light source within the photonic crystals, which is emitting at the band cap at 600 nanometer. And you do a large area measurements, you get this red curve here. Okay. And if you do look at the small region, which is a single domain, the resulting curve is a blue curve. And you can see that two things. One is there's a peak code slightly shifted, and you see there is a bit of suppression in the emission intensity. That means the dye molecule, which is supposed to emit at 600 nanometer, is unable to come out of the system. And that because this dye, the emission wavelength is comparable to the band gap wavelength. So to clearly to give a very clear picture of this result, what we do, we take intensity ratio, basically your emission from your sample and your reference emission. And if your sample does not change the emission properties, it looked like a reference sample only, you get 1 because your sample does not do any changes to the emission. But if intensity ratio goes below 1, that means emission from the sample is suppressed. So that's what we shown here. So in the blue curve, the emission is collected from a single domain of the photonic crystal. You can see that around 60% of the spontaneous emission is suppressed in intensity. Okay, so when you go from a large area measurement to a single domain measurements, so you can even get a close to 60-70% suppression, even though these samples are very less index contrast, because the samples are made using polymeric material. So the refractive index variation is quite small. So we don't expect too much changes, but because of the nice measurement, we could get this kind of emission suppression. Now the question is, do you get the suppression same everywhere in the crystal? The answer is no. Okay. So you take this kind of sample, you measure here, the hundreds of domain you measure, and you look at the histogram. There are domains which give you emission suppression close to 70%, but there are domains which even give you less than 30% or so. So it actually varies in the samples. And that happens in any nanophotonic structures because there will be a lot of variation in the thickness of the samples. So you need to have a very precise measurement where from exactly you do measurements. So the other thing is that I've shown you that, okay, the emission intensity is changed. But does it clearly say that the density of state is changed or density of state is reduced within the band gap? The answer is no, because emission intensity won't tell you there is a density of state change or not. It's simply a filter. If I increase the pump power, it still increase the emission or decrease the emission. That does not mean that the density of state changes. So what we need is we need to measure the decay rate. Okay, and the decay rate is related to the LDOS. For example, if you don't clearly get what is LDOS, a large LDOS means there are a lot of pathway for the light to propagate to the outside world. There are many ways light can take. If the LDOS is reduced, there is only 1 or 2 ways where light can get out of the system. So typically what we do, we take a sample, we excite with a pulse laser, and we measure the decay of the excited emitter. So you look at the intensity of the emitter light goes an exponential, and with the term gamma, and gamma is related to the density of photon state. This is what you did in your, if you have not done it, you look at your quantum mechanics, especially Griffith book, time-dependent perturbation theory. This equation is nicely derived there, starting with a 2-level system, and how the decay rate related to the density of photon states. So if I want to know whether density of photon state is changed, I need to measure the decay rate. So that's what we did next in the experiments. So we developed a time result setup where we can measure these kind of decay rates. So we build this setup and we measure a typical dye decay rate to check as our system works. And you get an exponential decay, and then you fit it with a nice curve to estimate the lifetime. And you calculate the residuals, basically the difference in the fit and the original data, and the residue is close to 0. That confirm, okay, your fit is quite okay with the system. And so I measure the decay rate first from the reference, which is a suspension. It gives you a nice decay. Basically, you excite here, the emitter goes to the excited state, and you have a watch. You are looking at how much time the emitter come down to the ground state. So it's around 25-30 nanosecond. The emitter is completely come down to the system. If you give again energy, it will go again to the excited states. So the black curve is the curve you get from a reference sample. And you fit, and you got a lifetime of 1.9 nanosecond, which is a typical lifetime of dye, which is done by anybody who work in this field. Okay. And then we measure this decay rate from the photonic crystal, which is emitting at the band gap. And what you see here is the emission decay rate is quite slow down here. It's not come fast like this. It's quite slow actually. And this, then you fit that, you got a lifetime of around 4.3 nanoseconds. That means the intrinsic lifetime of your emitter is 1.9 nanoseconds. By putting it within the band gap and emitting within the band gap, the lifetime is become 4.3 nanoseconds. The lifetime is increased. That means it stays at the excited state for more than what it's supposed to stay. And that's because there's no way it can come out. Now you may ask why it is not infinite, because these are real samples. There is always some pathway it can connect to the outside world because of the unwanted light scattering and all. So probably I can skip this curve. It's not required for the students, and because you don't have time also. And now the question is, do we get the lifetime everywhere like intensity? Again, answer is no. So we did lifetime of many places on the sample. So you can see that it has quite a broad distribution in that. But within one domain, the lifetime is quite higher for within the band gap compared to a wavelength outside the field. Then we look at the system, how this lifetime varies across the sample. And what we have is the lifetime is as a function of thickness of the sample. And it has the L is thickness and the LB is a normalized parameter of the sample. So it has got a little bit of a linear scaling in the system. So the L dose, the density states in a band gap, it's linearly scales with the thickness of your sample. So when we did this experiment, there was a thanks that there's a theoretical calculation published in a similar in a PRL, where it shows that in a photonic band gap, the density of states scales with the system size. And that's what precisely we measure in our experiments. But only difference is here is a 3-dimensional band gap, and we are only looking at one directions. But it actually giving a signature of the systems. So the conventional book says L dose depends on frequency and positions, but this result shows that it also depends on your system size. So we have published a couple of papers recently on that. So you can look into that if somebody is interested, or more detailed, elaborate explanation and experiments. So if everybody, people ask, what are the use of these things? So you have band gap, you can control spontaneous emissions. What's the purpose of that? So some of the applications I just listed here, and everybody knows fiber, the optical fibers, which works by total internal reflection. And you need a core, which need a high refractive index, and the cladding is a low refractive index in order to get the total internal reflection. And that it's a solid fiber where the light is propagating through a silica or a dielectric material, and it can have dispersion, it can have absorption, and so on and so forth. So can we think of a light guidance through an air without any medium? Can we think of? So this has actually put the people's STEM idea that why can't have a cladding as a photonic crystals? So you have a core, which is air, surrounded by a cladding, which is a photonic crystal, basically 2D photonic crystals. And you launch the light into the core, which is at the band gap of this cladding, and the light is trapped like band gap and it propagates. And you can also have a reverse thing, you can have a cladding as a photonic crystal, but the core is also a solid core fiber, solid as a core. And these systems are used what is called as photonic crystal fibers. And one of the applications which is now commercialized is the supercontinuum light sources. So you can replace your conventional white light sources, and you have very nice light sources using these kind of fibers in the laboratory. We have in our lab one of such sources, and many people. And these supercontinuum sources or PCF photonic crystal fibers are used for many biomedical clinical treatment and all those things. The other thing is that you can break this periodicity locally, you can create cavities, and you can get lasing, nanoscale lasing from these systems. And in the recent times, people are looking at how to club single atoms or single emitters to these kind of waveguides or these kind of structures made of photonic crystal cavities and generate on-demand single photon. Basically, you get a single photon when you want it. Okay, so basically these are quite useful for many quantum technological perspective and applications. So I'll talk about this in some other time separately about it. So how much time do I have?
So you have 10 more minutes.
Okay. So what I taught till now is how this photonic crystal and how it band gap forms. And one of the things which you notice in all these slides, all these presentation is that everything is ordered. And we talk about refractive index, which is quite ordered. So now I will take you a little bit from order to tailored disorder. I'll tell you why is a tailored disorder in things. Okay. So ordered photonics structures or the photonic band gap structures, you have periodic variation of dielectric constant, we have Bragg scattering, we have photonic band gap, we have inhibition of spontaneous emission. This is what we studied till now. Now, when you talk about disordered photonic structure, instead of periodic variation of dielectric constant, basically you have a random variation of dielectric constants. And instead of Bragg scattering, you may have multiple scattering because you don't have any preferential ordering. So the light can make a very crazy path within the system. Yeah. Instead of Bragg length, you have a scattering mean free path, how much distance between the two scattering events. And the phenomena like random lasing or Anderson localization, flight like Anderson localizer for electrons. So that's why these systems are quite interesting. Okay. So we'll show you some of our initial result on these directions. So we start with the perfect photonic crystals, like our sample, which I shown you, very nice one. And we do something to the system, again, chemically, we create some kind of disorder, which is not quite random, but at the locally they are connected. What we call is a short range ordered systems. Okay. So this is quite interesting in the recent years. what we call as a tailored disordered systems, and there are claims that tailored disordered sample even outperform the ordered systems. Okay, so let's see how we do that. And before doing that, disordered photonics is everywhere around us, even from the blue color of the sky. You can have a ballistic, single scattering, multiple scattering. You have these nice white butterflies. It look white because it's a multiple scattering system. And there are many creatures which has a very disordered structure in their wing scales, and that give them anti-reflection properties or antibacterial properties, which help them their survival. And some of these birds have a nice colorations also due to this kind of disorder, but with a correlated connected disorder. Okay, that be very, in a very layman language, the disorder quite connected by the things. Okay, you can see that there are a lot of papers recently published in this, and there are a lot of people trying to mimic these kind of structures in the laboratory, and we do the same thing what nature does with the light. Okay, so when you talk about disordered system, for those students who may be hearing first time, it's a random variation of refractive index or the scatters in with the material thick in a certain lambda. For example, in the Haryana, in our region, when we have winter, we can't see, right? We have a huge fog issue. We can't see somebody who's coming opposite to us. That is one of the best example of multiple scattering of light, because there is no propagation of light. Your light which is coming is multiply scattered. Okay, so that is a very simple example of multiple scattering of light. So these air droplets, which the water droplets, which have a random variation refractive index, like milk, paper, powders, all look white because of multiple scattering of light. So when you launch a light in a multiple scattering medium where there is a random variation of refractive index, the light get a very zigzag path in the system. And the distance between two scattering event is called a scattering mean free path. And after a certain distance of its scattering, it will randomize its propagations, and what we call is a transport mean free path. So if you have a disordered sample, you take our logo, you have a plain glass plate, and if you on top of that you make some disordered powder or sample, you can see that its transmission is faded, so you can't see the symbol. And if I increase the disorder, you can see that it's completely opaque, like a fog. You can't see what is behind it. Okay, so this is a simple example to show you that how the multiple scattering happens within the samples, within these white powders. So we did some, we take our ordered photonic crystal samples, and we did some crazy thing during the fabrication of that. And we got a structure which the disorder is quite not that random, but there are ordering locally, okay? Or we can tailor the disorder, okay? How do you know that structure has a short range order or locally there is order? So what we have is a same picture of our sample. So this is our photonic, the disordered sample, the same picture of the sample. What we calculate is a pair correlation function. Basically, I take a scatterer here. I'm looking how many scatters nearby. If there is a periodic. If it is a periodic, I get a huge oscillation because I can connect to the next sphere. I can connect to the next sphere like that. But if you look at the pair correlation function, what you see here is a bit of oscillation still 1 micron. That means there is an oscillations, or there is a short range periodicity preserved probably three length scales, 3 lattice constants. And if you look at the white powders like a chalk powder or paracetamol tablets or titanium powder, you don't see any such kind of oscillations because there is no scatterers connected adjacent to that. So this confirms that there is a bit of short range order present in this system. And then we understand what happens when you launch light into the system. And there was very surprising result for us. So what we did we give a sample here, and we launch a white light, and we measure an experiment called a total transmissions. Because your sample is a disordered sample, so you launch a light, you get reflection from all directions and transmission also in all directions. Because these are disordered, the light scattered in all random directions. Whereas when you have a perfect nice samples, you don't have much problem because most of the light comes in the straight line, in the ballistic direction. So to collect that all transmitted light, we use a system what is called an integrating sphere. Basically, you have a sample here, it impinges the light, it transmits all the light, and it gets multiply scattered inside the sphere, and finally it connects to the detector. So this is a result of our measurements. So when you don't have a short range order, the black curve, the transmission actually decreases with the wavelength as expected. But when we measure from our sample, what was really surprising to us that it shows a dip in transmission around 650 nanometer, just after 650 nanometer. And if you look at a sample same scatter, same material, made the long range ordered sample, which is photonic crystal, it exactly showed the dip at the transmission dip at a close to 650 nanometer. So we claim that our sample, because of the short range order, which has a Bragg-like scattering and will give a resonant frequency gap. So this is what we call as a frequency gap in short range ordered systems. To analyze that, we even develop a scattering model following these papers, and we have come up with a small equations by calculating the structure factor, because if there is a diffraction, there will be peak in structure factor. And you calculate the lambda of the gap, the frequency gap, and plotted with the diameter of the sphere. So you can see that like a photonic crystal, which I shown you, the frequency gap wavelength for the short range order sample also scales. It's linearly scaled. If I want a gap at here, I need to use this sphere diameter. And if I want a gap here, I need to use this sphere diameter. And we even estimated the scattering length scales, like the transpond mini-free path, it actually shows reduction within the frequency gap induced by the short range order. Okay, so I stop it here because it will be a bit more complicated for students. Some of you, if you are interested, either you look at these papers, is a very detailed calculation is given how all this mathematics is done. And now we are working how these systems are useful to control the emissions, and indeed our initial measurements very good, and it indeed changed the local density of photon states like a photonic crystals. So with that, I conclude. I hope I able to convey some important aspects of photonic crystals, how the band gap formations, and how important the optical instrumentation for these kind of experiments, so that sometimes we classify samples are not good. Sometimes maybe our capability to measure the signal is not limited. So we consider that, okay, this sample is not good, so it cannot be used for purpose. And I hope you are able to convey some basic aspects of how emission can be controlled, how a disorder can be created, and how to use the disorder to get properties similar to an ordered systems. So these are our papers published in this field in the last couple of years. And these are the main results which I discussed. And before I stop, I thank my students, the present students and former PhD students, and all the agencies who's funding the research in my lab, from especially my institute, the SERP, DST, Sonaganti Fellowship, and collaboration from Germany, Russia through international projects. And we also part of the National Initiative for Quantum Technologies, where we are using nanophotonic structures to solve some of the fundamental issues in the quantum technology, like high efficient generation of single photons, coupling the single emitters with the cavities, and which is funded by National Program on Quantum Technology. And we have quite good PhD and postdoc positions available. If some of students wanted to work in nanophotonics or quantum photonics, please do contact me. And I thank you for your time. Thank you for this opportunity. And if you have any questions, I would like to have a discussion.
Thank you, Professor Nair, for such a nice and informative presentation on the interesting topic of nanophotonics, and for sharing the ongoing research efforts in this field. So session is open for discussion and questions now. So let me take question from chat box. So Dr. Jaswant wants to know about the difference between 2D and 3D band gap. And he's asking how the 3D band gap measurement useful than 2D measurements.
Okay, so both as I said, in 2D photonic crystals, you have a periodic variation of dielectric constant 2 dimensions. And in 3D photonic crystals, the periodic variation in the 3 dimensions. So in a 2D photonic crystals, to measure the band gap, suppose I have a crystal and I need to measure in one direction. So first direction, then I need to measure the second direction. So what I do, I measure reflectivity from here, and I also measure reflectivity from here, and I see whether these reflectivity peaks are overlapped. That means if it is overlapped, the light at that wavelength cannot propagate whatever be the direction you launch it. So similarly in 3D photonic crystal, you have to do a direction dependent measurement. Each direction you have to measure. And since you're talking about light, you should also measure with polarization of the light. Okay, so you need to measure in all spatial directions, both angle and polarization independent reflectivity peak. Then you look for the overlapping, and you see that yes, I got an overlapping reflectivity band. irrespective of the angle or direction or the polarization, then you can claim that is I measured the band gap for light.
Okay, thank you, sir. So there is one more question from YouTube chat box. So how nanophotonics is linked with the question quantum optics?
Okay, for example, one of the main effort what going in quantum technology is to generate on-demand single photons at high emission rates. Suppose you have a single for your system, let's say a nitrogen vacancy sender, you have a single quantum emitter, it gives you a single photon emission at a lifetime of 20 nanoseconds, right? So can we trap these kind of quantum emitters in nanophotonic cavities to generate emission, let's say with a lifetime of 5 nanoseconds? So instead of getting 10 single photon per second, using these structures, you may get 100 single photons per second. And you can generate on demand, like you can switch it actually. When you say it will emit, when you don't say it does not emit. So that is where the nanophotonic system come into the quantum technologies or the what is called quantum photonics emerge actually.
Okay, so thank you. So there is one more question regarding the density of states. How density of states increase or decrease, or what's the reason behind this decrease and increase in density of states?
So in the case of band gap, at the band gap, the density of state will be, in ideal case, it will be 0 because there is no states, because density of state is a number of states within a frequency omega and omega plus d omega for an emitter can have a transition. So within the band gap, there is no available states. So there is no way you can have a density of states. But when you create a cavity, you basically you break the periodicity to create a cavity. You are making the most states because there is an allowed mode within the band gap now. So you can have the peak in density of states. So that way you can, using cavities, you can increase the density. Even within the band edge also, you get a slight increase in the density of states, like because of the low group velocity, because density of state is inversely proportional to the group velocity. You have like in condensed matter system, so you have the band edges, you have standing wave formations, so you get a bit of sharp density of states. But if you really deterministically wanted to increase density of photon state, you need to create a cavity within the photonic structures.
Okay, sir. So there is one, I think it's the last question. So it's regarding the decay time of photons. So basically they increase by optical methods. So if it's possible to create a perfectly ordered photonic structure, can we achieve fully controlled spontaneous emission?
In reality, no, because how perfect you make, you will always have certain disorder and unwanted scattering. The best what people achieved is around 400 times increase in lifetime. We got around only I don't know 14% or something, but there are people who reported using diamond-like photonic crystal, which is a silicon photonic crystal. This is the best photonic crystal you can make in the world because silicon has the highest refractive index possible in the near infrared. So ideally speaking, it's not possible to make infinite lifetimes, but you can get probably quite high compared to the reference sample, because if any real sample will have problems like the scattering and other things.
Okay. So we don't have any more questions. So let's thank Professor Rajesh. Thank you, sir, for taking time from your busy schedule. We really enjoyed your talk. So thank you so much, sir.
Yeah. Thank you all. Thank you for this opportunity.
So now I request Dr. Ramandeep Kumar, Department of Physics and Astrophysics, for a formal vote of thanks. Over to Dr. Raman.
Thank you, Dr. Meenu. I am audible?
Yes, I guess you are audible.
Okay, thank you. Good afternoon, everyone who joined us virtually. Professor Rajesh Nair, Speaker of the Day, Professor Vandana Nair, General Secretary, IPA, colleagues, and all the participants. It is such an honor for me to get the opportunity to offer a formal vote of thanks on behalf of the Department of Physics and Astrophysics. I would like to express my sincere gratitude to everyone for their presence and contribution in making this colloquium a great success. I would like to thank our Honorable Vice Chancellor, Professor Tankeshwar Kumar, for all the permissions and logistic support to host this colloquium. I extend my gratitude to our Honorable Speaker of the Day, Professor Rajesh Nair, to take out time from his busy schedule for this colloquium. Thank you, sir, for a very informative lecture on nanophotonics. I am pretty sure that participants have learned significantly from this lecture. A special thanks to Professor Vandana Nanal, General Secretary, IPA, and entire team of IPA for providing us opportunity to host this colloquium. We are looking forward to host and organize more events of this kind in the future, as well as in collaboration with IPA. I extend my gratitude to Professor Sunita Srivastava and Professor Sunil Kumar, Head Department of Physics and Astrophysics, for the essential support and guidance. I would also like to thank Dr. Meenu Thakur for hosting this colloquium in a beautiful manner, and Dr. Jaswant Jadhav for his assistance to make this event successful. Thank you, everyone, once again for making it a great success. Thank you.
Thank you, Dr. Raman. So session is formally over now. So thanks for joining us and listening to this interesting and informative colloquium. So we really appreciate your time. Have a nice weekend.
Okay, thank you.